Imagine an AI not just solving tricky code and math problems, but actually figuring out how to solve them completely on its own,
Yeah.
without a single human example to learn from. Sounds a bit like science fiction, maybe.
It really does.
But that's the core idea behind something pretty fascinating called absolute zero.
It is, yeah. It's a significant leap, really. So today we're doing a deep dive into absolute zero. It's a really novel way of training these powerful language models.
Right.
It kind of flips traditional AI learning on its head.
Hmm.
We'll get into how it works, what's so revolutionary, and, the challenges that are still there.
Exactly. So if you're curious about the real cutting edge of AI development, or you want to understand how the next generation of AI might be built, or maybe you're just fascinated by this idea of machines teaching themselves, then this deep dive is definitely for you. We've gone through the research,
Yeah.
pulled out the key insights to give you a clear picture of this zero data approach, the potential, but also, the limitations.
And just to be clear, our discussion is grounded in the research paper Absolute Zero, Reinforced Self-Play Reasoning with Zero Data. We've really dug into that paper to pull out the crucial bits for you.
Okay, great. Let's get into it then. So the fundamental idea behind absolute zero, it's not about feeding the AI tons of human-labeled data, right? It's using something called reinforced self-play. What does that actually mean in practice?
Right. So reinforced self-play at its heart means you have a single language model that's basically wearing two hats.
Okay.
It generates its own learning task, its own homework, if you like, and it turns around and tries to solve those same tasks.
Huh.
And the crucial part is how it learns. It uses feedback, but not from humans. It gets feedback from an external objective environment, like a code interpreter that can just run the code and say, yes, this works, or no, it doesn't.
So completely different from something like RLHF, reinforcement learning from human feedback, which we hear about a lot.
Exactly. RLHF relies heavily on humans, saying, I prefer this answer over that one. This cuts humans out of that specific loop during training.
No human guidance during the actual learning phase itself.
Precisely. And the engine driving this is called the Absolute Zero Reasoner, or AZR. It's this unified language model
Right, AZR.
that acts as both the teacher proposing the tasks and the student trying to solve them, all in one model.
Okay, so this AZR model has this dual role. Now, you mentioned AlphaZero before we started recording, the AI that mastered Go. How does this reinforced self-play connect to that? Is it a similar idea?
It's a very similar principle, yeah.
Yeah.
Think about AlphaZero playing Go or chess. It didn't learn from databases of human games.
Right, it just played itself
Yeah.
millions of times.
Exactly. It played against itself, learned which moves led to wins, which led to losses. Absolute Zero applies that same kind of logic, but not to a board game.
Okay.
It applies it to reasoning tasks. So instead of game scenarios, the AZR model generates its own, let's call them reasoning scenarios, like coding problems or math proofs.
Ah, I see.
And it learns from the outcome, did it solve the coding problem correctly, according to the code executor. So, yeah, it's like a game AI. But the game is learning to reason effectively in these complex domains.
That's actually a really clear analogy. Playing against the problem itself. Okay. And the name Absolute Zero, it points to this zero data aspect. Can we just clarify exactly what zero data means here? Because people might think of zero shot.
That's a really important distinction to make, yeah. Zero data learning in this specific context means training the model or fine-tuning it without using any external data sets that have been labeled or curated by humans for that task.
Okay.
The model learns purely from the data it generates itself through this self-play process.
Right.
Now, that's different from zero-shot inference, which is about whether a model, after it's been trained, can tackle a completely new type of task it's never seen before without any further training examples for that specific new task.
Got it. So zero data here is about the training input, not the inference capability later on. It learns without human examples during training.
Exactly. The zero refers to the source of the training data for the reasoning skills. Yeah. It's all self-created.
Okay, that's clear. Now, we mentioned RLHF used in models like ChatGPT. What are the known limitations of those kinds of traditional RL methods that Absolute Zero is trying to, well, solve?
Right. So traditional RL approaches in LLMs, including RLHF, they've been incredibly successful, no doubt,
Okay.
but they do have limitations. A big one is just the sheer scale and cost of the data needed.
Mm-hmm.
RLHF needs a lot of human preference judgments. Is this answer better than that one? That takes time and money. And task-specific RL often needs predefined tasks and maybe even handcrafted reward functions.
Right.
This reliance on human input, whether it's preferences or task design, can be a bottleneck. It can limit scalability, especially for really complex reasoning.
And doesn't relying on humans also risk baking in our biases?
Absolutely, that's a major concern. Human feedback inevitably carries biases, conscious or unconscious, and the RL process can amplify those. Plus, designing good reward functions for language is notoriously tricky. You want the model to learn genuine understanding, but it might find clever shortcuts to maximize the reward without actually getting smarter. That's the classic reward hacking problem.
Yeah, we've definitely seen examples where AI seems to game the system it's given. So how does Absolute Zero try to sidestep these issues?
The core strategy of Absolute Zero is to bypass these problems by removing that direct dependence on external human data and critically manually designed reward signals based on human judgment.
Okay.
By having the model generate its own tasks and then using clear, objective feedback from a verifiable environment like that code executor that just says pass or fail.
Right, no ambiguity.
Exactly. The goal is to create a more self-sufficient learning process, one that's hopefully less prone to human bias and less susceptible to reward hacking because the feedback is grounded in objective reality.
Okay, so the AI is its own teacher and student, setting homework, trying it, and getting graded by a neutral, automated judge. Let's unpack that propose, solve, learn cycle you mentioned. What happens in the propose phase?
Okay, so in the propose phase, the AZR model, wearing its teacher hat, generates a bunch of potential learning tasks.
Right.
The research paper focused heavily on code-based reasoning problems. Things like write a Python function to do X, or here's some buggy code, fix it.
Okay, coding tasks.
Yeah, but interestingly, they structured these tasks around three fundamental modes of reasoning: deduction, abduction, and induction.
Deduction, abduction, induction. Okay, those sound like, well, fundamental logic concepts. How do they apply to code?
Think of it like this. Deduction is forward reasoning. Given the code and an input, predict the output. Pretty straightforward.
Like running the code in your head.
Kind of, yeah. Abduction is backward reasoning. Given the code and the output, what input could have produced that? It's more about inference.
Ah, okay. Inferring the cause.
Exactly. And induction is about generalization. Given some input-output examples, can you write the code, the function, that performs that mapping?
So seeing a pattern and writing the rule.
Precisely. By generating tasks across these three modes, the model isn't just learning one way to solve problems, it's practicing different cognitive muscles, if you will.
That's really interesting. It's learning to think in different ways using code as the medium.
That's a good way to put it. It forces a more general understanding.
Okay, so the model proposes these varied coding challenges, but how does it know if these are good challenges? Not too easy, not impossibly hard?
This is where a really clever part comes in. It's called the learnability reward.
Learnability reward.
Yeah. After the teacher part proposes a task, it doesn't just get thrown to the student. First, the environment, the code executor in this case, checks if the task is even valid, like does the description make sense? But it also estimates how difficult that task is likely to be for the current state of the student model.
Okay, how does it estimate difficulty?
The paper mentions using Monte Carlo rollouts. Basically, it tries solving the proposed task internally, maybe a few times, really quickly.
Like a mini test run.
Exactly. To see how often the current student version would likely succeed. And the key is, the teacher gets rewarded most for creating tasks that are in that sweet spot, sometimes solvable, sometimes not. The Goldilocks zone of difficulty.
Not too easy, not too hard, but just right for learning.
Precisely. Because if it's too easy, the student doesn't learn much. If it's too hard, the student gets frustrated and learns nothing. This reward pushes the proposer to generate tasks that maximize the learning progress for the solver.
That is really smart. It's like the AI is tuning its own curriculum automatically based on its current abilities. Okay, so a good learnable task is proposed. Now the solve phase.
Right. Now the same AZR model, switching to its student hat, actually attempts to solve that task. If it's a coding task, it generates the code it thinks is the solution.
Yeah, okay.
Once it produces a solution, that solution gets passed to the environment, the code executor.
And the executor just gives it a thumbs up or thumbs down.
Pretty much. It provides very simple, binary solution accuracy reward. It's a 1 if the solution is correct, the code runs, passes, tests, whatever the criteria are, and a 0 if it's incorrect.
Clean, objective feedback again.
Very clean. No ambiguity about whether the goal was achieved for that specific task.
Okay, propose, solve. Now, the joint update and the learn part. How does the model actually internalize all this? How does it get better?
So after both the propose and solve phases are done,
Yes.
and you have these two rewards, the learnability reward for the proposer and the accuracy reward for the solver, the model's internal parameters, its weights, get adjusted.
Right.
The paper mentions using an algorithm called TRR plus J. Don't need to get into the weeds, but it's essentially a specialized reinforcement learning algorithm designed for this kind of dual role self-play setup. What it does, fundamentally, is reinforce the actions that led to higher rewards. So the model becomes slightly more likely to propose tasks deemed learnable and slightly more likely to generate correct solutions for those tasks. It's learning both skills teaching and solving simultaneously.
And this whole cycle just repeats. Propose, solve, update, propose better, solve better.
Exactly. It's a continuous loop. The model starts, presumably, with very simple tasks. As it gets better at solving them, the learnability reward encourages the proposer to generate slightly harder tasks, pushing the boundary outwards.
Wow.
And the system can also keep a memory of past tasks and solutions, which helps encourage diversity and stops it from just generating the same easy problems over and over.
And this really brings us back to that AlphaZero comparison, doesn't it?
It absolutely does. It reinforces that core idea. Learning by inventing and then mastering your own challenges. AlphaZero did it with game positions. Absolute Zero is doing it with reasoning problems in code and math.
And that verifiable environment, the code executor, is the crucial anchor. It's the objective referee. It's absolutely vital. That grounding in objective, verifiable outcomes is what helps it avoid the pitfalls of purely subjective feedback or reward models that an AI might learn to manipulate without actually understanding.
Okay, this process makes a lot of sense now. We see how it learns. Let's talk more about the capabilities, especially these different reasoning modes. You mentioned deduction, abduction, induction.
Right. Well, one key architectural point is that AZR uses that single transformer model for both proposing and solving.
Yeah, you mentioned that, the two hats.
That's important because it allows for very efficient knowledge sharing. What the model learns while trying to solve a tricky induction problem can directly inform how it later proposes new, more effective abduction tasks, and vice versa. The learning is shared across roles.
Ah, okay. So the teacher benefits from the student's struggles and successes.
Instantly. And these specific reasoning modes, deduction, abduction, induction, how do they build overall capability?
Yeah.
By making the model practice all three, it develops a much more rounded, robust understanding of the domain, which here is primarily code.
Right. Deduction trains logical execution. Abduction trains inferential, maybe even creative, problem solving working backwards. And induction trains generalization, pattern recognition, synthesis.
So it's not just learning to code, it's learning different facets of logical reasoning through code.
Exactly. It's building a more general reasoning toolkit, not just becoming a glorified code completion engine. It has to understand the structure and logic much more deeply to succeed at abduction and induction tasks generated through self-play.
It's really exercising different cognitive pathways.
That's a great way to put it. And because the feedback comes from actual code execution, the reasoning it learns is grounded and transferable, not just based on statistical patterns in text.
That sounds much more powerful in the long run. Okay, so how does absolute zero stack up against other common methods? You mentioned RLHF. How different is it really?
The difference is pretty stark. With RLHF, the model is mostly a solver. It responds to external prompts, often from humans, and then gets judged by a separate reward model that was trained on human preferences. AZR, on the other hand, generates its own prompts, its own tasks, and its reward comes directly from the environment's objective feedback, not a separate preference model.
Okay, clear difference there. What about methods like self-instruct or generating synthetic data? Those also involve AI generating data, don't they?
They do, but the mechanism is quite different. Self-instruct and similar techniques typically generate a large static data set of instructions or examples up front.
Like a one-off data creation step.
Exactly. You generate the data set, then you train the model on it, maybe using standard supervised learning. AZR's self-play is fundamentally different because it's dynamic and part of the training loop itself.
Ah.
The task generation, solving, and learning happen continuously and iteratively, with explicit rewards shaping the process and an emergent curriculum. It's not just creating a fixed data set beforehand.
Got it. It's a live, ongoing process. And what about automated curriculum learning in more traditional RL? Hasn't that been explored?
Yes, automated curriculum learning is a concept in RL, but AZR really brings it fully into the LLM reasoning space in a novel way. Often, curriculum learning involves selecting tasks of increasing difficulty from a pre-existing, maybe very large set.
Right, selecting, not creating.
Exactly. AZR has the model generate the curriculum itself, tailored to its current ability level via that learnability reward.
We can compare it to something like Ace Coder.
Okay, Ace Coder.
Ace Coder was an interesting prior work that used RL for code generation. It automated the generation of test cases to evaluate the code,
Ah,
but
yeah.
it still relied on a set of coding problems curated by humans. AZR takes the next step by having the AI generate the problems as well as the solutions.
So AZR is really focused on this deep single-agent self-improvement loop, generating its own challenges rather than just solving external ones or debating answers.
Precisely. It's about skill acquisition through self-challenge against the inherent difficulty of problems judged by reality.
Okay, that clarifies the distinctions. Now the big question, how well does it actually perform? What are the results? Well, the claims in the paper are pretty bold. They report state-of-the-art results at the time of publication on several challenging coding benchmarks like Human Evil Plus and MBPPP,
Okay.
and also on math reasoning benchmarks, including problems from AMC competitions and even Olympiads. And this is the key part. Achieving these results despite having zero human-provided training examples specifically for these benchmark tasks.
That is quite a claim. State of the art without seeing human solutions for those specific types of problems. How does that compare to what people previously called zero-shot performance?
It's different. Often previous zero-shot work still involved fine-tuning on a broad set of human-generated instructions or tasks, hoping for generalization. AZR is distinct because the fine-tuning itself happens without any human-written tasks related to the target evaluation domains. It learns the reasoning skills purely from self-play on code.
And how did it do against models that were trained on human code data, like maybe similar-sized models?
The paper showed that their AZR model, specifically a 14 billion parameter version, outperformed comparable sized models that were trained or fine-tuned on human code datasets, like the Ace Coder model we just mentioned, on those specific benchmarks. Now, of course, much larger proprietary models like GPT-4 might still achieve higher absolute scores overall.
Sure.
But the key point is that AZR achieves very strong, even state-of-the-art performance for its size class, using this completely different zero human data training paradigm for the reasoning part.
So really impressive results demonstrating the power of the self-play approach. Who are the main players pushing these kinds of ideas forward?
Well, obviously, the researchers behind the Absolute Zero paper. Then you have related work like Tiger Lab, who did Ace Coder, focusing on RL for code generation.
Right.
And you can bet that major labs like OpenAI and DeepMind are actively exploring various forms of self-generation and synthetic data, even if their exact methods differ.
Makes sense.
And maybe slightly adjacent, but relevant in reducing reliance on direct human labeling, is Anthropic's work on constitutional AI, which uses AI feedback rather than human feedback for alignment.
Okay. And how mature is this specific AZR technology? Is it ready for prime time?
I'd say AZR, as presented, is still fundamentally a research prototype.
Okay.
It's shown promise and demonstrated effectiveness across different model scales in the paper, but more research is definitely needed on scaling it up to the absolute largest models and applying it robustly to domains beyond code and math where verification is harder.
So a very promising direction, but still early days in terms of widespread application.
That's a fair assessment.
This is really fascinating stuff. Let's distill the key benefits. What's the big value proposition here for you, the listener, to understand?
I think the most striking benefit is the potential to eliminate the need for massive, expensive human-labeled data sets for teaching reasoning skills.
That's huge.
It really is. It addresses a major bottleneck in AI development. It could potentially lower costs dramatically and accelerate progress, maybe even allow smaller labs or research groups to train highly capable models without needing Google-level data resources.
That could democratize things quite a bit. What else?
There's the continual learning aspect, driven by that auto curriculum. The model is constantly pushing itself with tasks at the right difficulty level. This should lead to very efficient learning. Every training step is potentially highly informative, unlike just churning through a massive static data set.
Okay, efficient learning.
We also saw evidence of strong generalization, good performance on unseen problems. That's likely because the self-generated tasks are diverse and force a deeper understanding than just memorizing specific human examples.
And you mentioned the feedback mechanism is more reliable.
Yes, using verifiable environments like code execution gives a much cleaner, less noisy reward signal compared to subjective human preferences. This reduces the risk of reward hacking.
Right. No gaming the human.
Right.
That all sounds incredibly positive. What about bias? Does this help?
There's a potential for bias reduction. By relying less on vast amounts of human language data, which inevitably contains societal biases, models trained this way might inherit fewer of those human-like reasoning biases. That's still an area needing more study, though.
Interesting potential.
And of course, the strong benchmark results themselves are a key benefit. It demonstrably works well. Plus, the core method seems like it could potentially be applied to different underlying language model architectures. It's not necessarily tied to one specific type of transformer.
So summing up the benefits, potentially cheaper and faster development, better generalization, more reliable and efficient learning, maybe less bias, proven performance, and architectural flexibility. That's quite a list.
It is. It presents a compelling alternative paradigm.
So if this pans out, what are some real-world applications we might start to see emerging from this kind of self-learning AI?
Well, the most direct applications are in the areas it was tested: coding and math. You could imagine much more advanced code assistants, maybe even steps towards autonomous coders that can continuously improve themselves or adapt to new programming languages and APIs through self-play.
AI learning new coding tricks on its own.
Yeah, and autonomous testing, finding bugs, optimizing code. In math, you could have AI tutors that generate personalized practice problems perfectly tuned to a student's level, or assistants for mathematicians exploring complex proofs.
Okay, coding and math makes sense. Anywhere else?
The key is the need for a verifiable environment. So think about training AI in simulation for real-world tasks where success is clear-cut. Robotics, perhaps.
How so?
Imagine an AI learning assembly tasks in a physics simulator. It could propose assembly strategies, try them out, and the simulator provides objective feedback. Did the object get assembled correctly without breaking?
Ah, okay. Assembly, maybe logistics, cybersecurity tasks where you can verify if a defense worked or an attack was found.
Exactly. Anywhere you can define success objectively and automatically. Another area is adapting models to specialized data-scarce domains.
Like medicine or law.
Potentially. If you can build an environment that incorporates domain knowledge, say a medical knowledge base or a legal simulator, the AI could generate synthetic case studies or problems, try to solve them, and get verified against that knowledge base, even without large real-world data sets from that domain.
Interesting. Like bootstrapping knowledge in niche areas.
Right. And maybe even deployed systems that continue to learn and improve in the background, using self-play on relevant tasks, continuous improvement.
AI that gets smarter while it's working.
That's the dream. It could also be used simply to benchmark AI's ability to learn autonomously, pushing AI R&D itself, or even collaborative problem solving, where the AI proposes interesting subproblems or test cases for humans to consider.
You could imagine an AI helping optimize complex systems like, say, SQL database queries.
That's a perfect example. The database system itself is the verifiable environment. The AI could propose query variations, run them, get performance feedback, and learn to optimize purely through self-play against the database.
The potential applications are really broad, assuming that verification piece is possible. But like any powerful new tech, there must be significant challenges and limitations too, right?
Oh, absolutely. It's not a silver bullet. The biggest hurdle, as we've touched on, is that dependence on having a verifiable environment.
Right.
That currently limits its applicability. It's great for code, math, maybe some simulated physics or game environments. But how do you get objective automatic feedback for, say, writing a good poem, or having an empathetic conversation, or summarizing a nuanced political argument?
Yeah, much harder to get a simple correct or incorrect.
Exactly. So its applicability to more open-ended, subjective domains is a major question mark for this specific pure self-play approach.
What other challenges are there?
The quality of the self-generated tasks is critical. If the proposer isn't rewarded correctly, it might generate uselessly trivial tasks, or impossibly hard ones, or just get stuck in a rut. Ensuring the tasks drive productive learning requires very careful design of that learnability reward.
It sounds like getting that reward function right is still key, even if it's not directly from humans.
It is. It shifts the difficulty from gathering human preference data to designing effective self-play dynamics and rewards. Also, computational cost.
Ah, is it expensive to run?
Self-play RL can be extremely computationally intensive. You're not just training the model, you're constantly running this propose, solve, evaluate loop, interacting with the environment. It can require a lot of compute.
Okay, so potentially costly. What about stability? RL can sometimes be unstable, right?
Yes, that's another challenge. ensuring the model learns consistently without the learning process diverging or the model forgetting previously learned skills, or finding ways to hack the learnability or accuracy rewards that requires careful algorithmic design and tuning.
And are the skills it learns truly general, or are they tied too closely to the kinds of tasks it generates for itself?
That's a valid concern. If the task generation isn't diverse enough, the learned skills might be narrower than desired. Ensuring a broad range of self-generated challenges is crucial for developing truly general reasoning abilities.
Right. And how does this whole approach scale with model size? Do we know if it works as well for truly massive frontier models?
That's another area needing more research. The paper showed scaling across some sizes, but how well self-play competes with or complements learning from vast external data at the scale of hundreds of billions or trillions of parameters is still an open question. There might be diminishing returns compared to just soaking up more knowledge from the web.
Okay. Any ethical or safety concerns specific to self-play?
Well, in open-ended domains, if you didn't have strong constraints, there's a theoretical risk that self-play could lead a model to discover or optimize for harmful knowledge or strategies if the environment and rewards weren't carefully designed with safety in mind.
Something to watch.
And alignment. Models trained purely without human interaction data might develop capabilities but not necessarily behave in ways humans expect or prefer. The reasoning might be effective, but alien. So alignment with human values and interaction styles is still a separate challenge that self-play alone doesn't solve.
Right. It learns to be good at the task, but not necessarily good at interacting with us about it.
Exactly. And finally, reproducibility. These complex training loops can be harder to set up, debug, and reproduce compared to simpler supervised training. It adds complexity to the MLO's pipeline.
So it definitely shifts the problem space. Less about data collection, more about environment building, reward shaping, and managing complex RL dynamics.
That's a perfect summary of the trade-offs.
Okay, acknowledging those challenges, what's the future outlook? Where might this research direction head next?
I think a major thrust will be trying to expand the reach of self-play beyond easily verifiable domains. This likely means developing more sophisticated automatic evaluators or simulated environments for things like dialogue, summarization, or creative writing.
Using AI to judge AI more effectively.
Precisely. Another big trend will likely be hybrid approaches, combining the strengths of self-play for capability building with techniques like RLHF or instruction following for alignment and controllability, getting the best of both worlds.
Makes sense.
We'll also see much more research into the scaling laws of self-play. How does performance really scale with model size and compute investment in this paradigm? That will determine how widely it gets adopted.
Right. Understanding the economics of it.
We might even see specialized automated curriculum agents, AI systems, whose sole job is to generate optimal learning tasks for other AIs.
Wow. AI teachers for AI students.
Yeah, and integrating self-play with tool use and agentic AI seems natural. Agents that learn to achieve goals by setting their own sub-goals, trying actions using tools, and learning from the outcomes via self-play.
That sounds like a path towards more autonomous systems.
It does. And potentially, using self-play for safety and alignment itself, maybe AI agents designed to constantly stress test each other, find vulnerabilities, and improve robustness through adversarial self-play.
Using the technique to make AI safer.
Potentially. And then there's the really exciting blue sky possibility.
Yeah.
Could self-play lead to the emergence of genuinely novel skills or knowledge? Discovering new algorithms, mathematical proofs, scientific insights that are beyond current human understanding because the AI explored spaces we haven't.
That's the really profound potential, isn't it?
It is. And more practically, we'll probably see efforts to integrate these self-play techniques into standard AI development pipelines, making them easier for engineers to use. And of course, regulators and ethicists will need to evolve oversight mechanisms for these kinds of continuously self-improving systems.
Absolutely. It feels like we're really just scratching the surface of what self-learning AI could mean.
I think so too.
Well, this has been an absolutely fantastic deep dive into Absolute Zero. It really feels like it represents a potential paradigm shift in how we train large language models, demonstrating the power of reinforced self-play and these verifiable rewards
Hmm.
to achieve really high levels of reasoning, especially in domains like code and math, crucially, without needing that human-provided training data for the specific tasks.
That's the core takeaway.
Yeah.
And for you listening, understanding absolute zero really offers a glimpse into a possible future for AI development, a future where models learn much more autonomously.
Yeah.
And that could have huge impacts on applications, maybe lower barriers to entry, and really change the landscape of AI capabilities.
It leaves you with a really provocative thought, doesn't it? Could the most effective teachers for AI ultimately be other AIs, pushing boundaries beyond what human-curated knowledge alone can achieve?
Right.
And what completely new abilities might emerge when AI truly learns how to learn on its own terms?
Those are the big, fascinating questions that methods like absolute zero force us to confront. It's an exciting time. We definitely encourage you to look deeper into the research around absolute zero and these related zero data or self-play learning methods.
Definitely food for thought. Consider the implications, the potential, and also those significant challenges that still need solutions. As always, we welcome your thoughts as we continue exploring these incredible frontiers together.